mismatch and space penalties. Okay? You might ask why I don't put something on matches here, right? X, Y, Z. Why don't I play around with the value of a match? What's the answer to that? Yeah, you can conceptually think about it and say, yes, this is really a parameter here, here's a parameter. There are really 3 parameters. But for any choices of X, Y, and Z, if I just divide here by Z, when this one goes back to being 1, this is X over Z, this is Y over Z. And that's just a different, since I'm going to let this parameter run through its all possible ranges, it really doesn't matter whether I call it X divided by Z or just call it X. Okay, so another slightly less clumsy way of saying this is there are only 2 independent parameters here. If I have 3, I can think conceptually having 3, but there's only 2 that are independent. I get the full range of behavior by setting this to 1. Anyway, and then from a practical standpoint, it's good to only have 2 parameters because on a computer screen you only have 2 dimensions. There are actually programs that will show this kind of thing in 3 dimensions, or this 3-dimensional representation, but you don't need to when you only have matches, mismatches, and spaces. 2 parameters are enough. Okay, so multipliers on mismatch. That's another way people got to richer models that hopefully found alignments that were more meaningful from a biological standpoint. And part of your exercise this week has you playing around with this model, okay, without any further embellishments. Now, what I think Fitch did in the early 1980s somewhere is he had, there wasn't a lot of data then, but he had 2 fairly short sequences where he felt that he knew what the right alignment was. I mean, the alignment that meant something biologically. And he wanted to see how good is this technology, this alignment business that people were all starting to do. And now we just do massively. And what he did was he took his example, his 2 sequences. Let me just clean this up a little bit. Number of mismatches minus number of spaces. And yeah, he multiplied by X, multiplied by Y. And by hand, he did what XParal does now automatically. He computed this nice decomposition of XY space, where he could see all of the possible alignments, all of the alignments that maximized this objective function over all choices of X and Y. So whenever you fix a particular value of X and Y, then you have a specific optimization question, and you can find through the method I haven't told you about, but you can find the alignment that maximizes that objective. And he did that for all X and Y in a systematic way that XParal now does automatically. And he looked at all those alignments, and he found that none of them were really satisfactory in terms of capturing the alignment that he thought was right, that he thought was biologically relevant. And that led him, and others, he wasn't the only person, into this notion of gaps. So that's the second way that the model is enriched, particularly for protein. Okay, so what is a gap? Here's a definition. A gap is a contiguous sequence or interval of spaces. Okay, so if I have, let's say, A against A, and then 3 spaces here, B, X, Y, Z, Z, W, P. Okay. This is an alignment that has however many matches it has, however many mismatches it has, but it has 1, 2, 3, 4, 5, 6 spaces, and only 4 gaps. Oh, sorry, 3 gaps. So the 6 spaces are organized into 3 gaps. And 1 gap here, 1 gap here, even though there's just a single space, it's nonetheless a gap. And here's a longer gap. So you can have different alignments that have exactly the same number of matches, mismatches, and spaces, but with different numbers of gaps. The spaces are organized into different number of gaps, and the way they're organized into intervals can differ. And what he was asserting, particularly in protein, is that an alignment that sprinkles the spaces all over the place doesn't look very real, doesn't reflect the biology that he knows, doesn't reflect how 2 sequences that are related to each other by biological processes ought to look when you do the best possible alignment. In his view, they should have just a few gaps. They may be very long, or they may be very short, but the spaces should typically be organized into runs or intervals of gaps. So he then, remember, he looked at this objective function in completion. So I'm moving back over here now if you want to. Thank you. He looked at this model. This is a model. It has no, this is a mathematical model associated with a algorithmic problem. But it has no notion of a gap in there. Even though it has X and Y, it has no notion of a gap. It can multiply mismatches in spaces, so he has a way of fine-tuning that. But even with all the fine-tuning that he did, he couldn't get an alignment that recreated the alignment that he thought was meaningful. And so he and others, at that point, introduced into the objective function this further term, which is subtract off something for gaps. Okay? You don't want to have a lot of gaps. So we're trying to maximize, we're trying to make this big. You want a lot of matches, you don't really want a lot of mismatches, you don't really want a lot of spaces, but you'd also like to control how many gaps you have. Okay? And he was, at the time, wearing that t-shirt. Would you stand up and, yes. You know, yeah, you know you're wearing, and face the camera. And anyway, the camera should capture that one. I guess the camera's not listening. Anyway, he thought it was important to mind the gap. Which is what that T-shirt says. And how many people know where that comes from, by the way? Just an odd question. Only one or two? Yeah, it comes from the underground in London, where they have it as you get off the train. It's stenciled there almost every exit, so you don't fall through or fall too far. Anyway, they make those T-shirts everywhere. So if you ever pick up one. So anyway, they introduced the notion of gaps. So you don't want to have a lot of gaps, and you can control things to some extent by including this in here. Well, the next obvious step is gaps and a multiplier on the number of gaps. So now we have x, y, and z. How do I get my y inside there? That was silly. Y times the number of spaces. So z times the number of gaps. So now that we have 4 elements of an objective function with matches, mismatches, spaces, and gaps, now we do have 3 independent variables. And we would like to have a multiplier x, y, and z. And that's why some parametric programs actually would like to display this in 3 dimensions, showing x's for x, y, and z. Xparallel only shows things in 2 dimensions, and you have in your menu your choices. You have to decide which 2 out of these 4 you're going to parameterize. Okay, so what Fitch next did is he parameterized these 2, I believe. You can see in the notes, y and z. And just forget x because that used to go there. And by playing with y and z, and for each setting of y and z finding the best alignment, the alignment that maximizes this objective function, he was able to find an alignment that recreated the alignment that he thought was right. And so in your homework, in your exercise this week, you should be able to do that as well. And the same thing with the Barton data. That's more complex. It's a much longer sequence, but you should be able, after failing to recreate the alignment that Barton starts with, or by many settings and different models that seem to give you too many choices, and so on, you should eventually, with the right model, be able to get an alignment that seems right in comparison to the Barton's alignment. Okay, and actually for the Barton, there's a third very important element that makes richer models, and that is substitution. Substitution, I forget what we call it in XPRL, but generally we call it substitution matrices. I think in XPRL it's called something else. But anyway. So substitution matrices, I mentioned this briefly today in lab, and we'll talk about this more throughout the quarter because it's a question of where do these things come from? How do you get good substitution matrices? But what this is saying is that not all mismatches, and in fact not all matches, are of equal significance. So a mismatch in alignment that matches, for example, isoleucine to leucine is not a huge, you don't have to invent a huge, difficult biological story for how that happened. You can still imagine the 2 sequences where they have this kind of a mismatch are highly related, because these are 2 amino acids that are quite similar and that mutate one to the other fairly easily. And therefore, this kind of mismatch should be less penalized. Should be less penalized than a mismatch, say, of tyrosine. Is this tyrosine? And tyrosine is a Y. Okay. And what's a G? Glycine. So this is big and this is small. And there are other ways that you can find 2 amino acids. One's charged, one's not, and so on. Hydrophobic, hydrophilic, etc. 2 that are quite different, where a mismatch between those is postulating a large chemical and biological change, and therefore probably should be penalized much more than this kind of a mutation. And so what you have are substitution matrices that encode all of those. So you just have, this is particularly true for amino acids, but it's also true in terms of DNA as well. So you have all of the amino acids and so on, the 20 here and 20 here. These are the identities along here. And some value for particular mismatches that will be found in this matrix. Okay? And even some value for matches that are found in the matrix. Now, generally, the values for matches are going to be positive, and the values for mismatches are going to be negative. I should have told you exactly how this is used. When you have an alignment, the score you give for that alignment is no longer just the number of matches. It doesn't start out just with the number of matches, but it is the score that's taken from the summation of the values that are taken from this matrix corresponding to the matches that you actually have in there. So over here, well, this is not an amino acid because B is not, maybe there's some other ways in which this is, anyway, just imagine it was. So you have a match of A to A, and you go into the substitution matrix and you'd say, you find out what value does an A match have. So that contributes to the value for the match element. What do you get from a Z, what do you get from a P, and so on. And those are taken from that particular substitution matrix. And then mismatches, you would also go into the substitution matrix and you'd find the QR value. And that would then be taken, if the mismatches are negative, that's actually as a plus. And in fact, if you look at XPRL, one of the windows, the objective function windows, has number of matches plus number of mismatches. And that has a subtraction for spaces. And I think I mumbled something in the notes about how that's kind of an error. But really what it is just, it reflects the fact that the values for mismatches in the matrices are already negative. And so we're really just, from an So we don't want to subtract a negative because then it'll become positive. But the spaces still are subtracted off. Okay, so the substitution matrices are very, very critical in terms of getting the right alignments, getting alignments that are biologically meaningful. And again, this week's exercise is to get you to sort of discover how important all of the pieces of the model are in order to get a good alignment, a biologically meaningful alignment. There are many substitution matrices that have been proposed out there. The one that you're using in the exercise is something called PAM 250 plus 8. And it's in a file that's in the directory that you're working in. You can actually just look at that file and you will see what the values are. You have the two coordinates on that array that's in there, and you can see what the values are. Now, the PAM matrices we'll talk about later, how they were constructed. It's a whole series of matrices, and this sort of indicates which PAM matrix it is. The plus 8 means they took the original PAM matrix and they added 8 to all values. A little bit of alchemy. But today, and PAM 250 used to be the default matrix that a lot of people would use when they didn't know any other one that was better. Today, this is a little bit dated. And people tend to use the Blossom series of matrices, which we'll talk about also later in the quarter, where these things come from. But I don't have that built in. You can use it. I'll make it available. And in XParallel, when it asks for what scoring matrix, there's an option for other. And as long as you have it in that directory in the right form, you can use it. So you can try that out if you like. Blossom 62, I think, is now sort of the default. When you don't know anything else to use, people tend to use that one. But we'll talk more about these. I just want to say that, particularly for protein comparisons, DNA is somewhat different. But for protein comparisons, all of these features of the model are really have ended up being critical in terms of reliably getting back good alignments. And probably the most important are in opposite order here from the way I've done it. The substitution matrix is really important. Gaps in the model tend to be significant, very important. And then the actual multipliers more fine-tune things. Now let me just tell you some terminology and then I'll tell you the although. When you're looking at protein under this model, gaps, the gap Z is oftentimes called the gap initiation cost. Okay, and you'll see that referred to in the XParallel notes, and you'll see that in biological literature. So that is what it costs you for a gap. So if you think about starting a gap, and you don't know how long it's going to be, but there's going to be a gap, then you can think about initiating a gap without knowing how long it is. Okay, so that's why it's called a gap initiation. What you pay for a single gap is Z here, and whatever you set Z to is the specific gap initiation. And then Y is referred to as gap extension cost, or penalty, cost penalty. Extension cost. Okay? And again, if you think about this, when you start a gap, you have to pay to start it, but you don't know how long it is. Every time you add a space to it, you're extending it. And you have to pay Y for each one of those spaces. So that's called gap extension. Okay? I think it's simpler just to say there's a cost for the spaces and a cost for the gap. But historically, those two terms have come up, gap extension for spaces and gap initiation for cost. Now, the although is that even though people don't always play around with Y and Z the way XParallel allows you to, there are definitely beliefs about the rule of thumb out there for how Y and Z ought to relate to each other. And some of these have become almost gospel. But if you go back to where the advised value of Y and Z came from, in many cases it came from somebody sort of off the top of their head. They said, let's try Y of 1 and Z of 12. Something like that. And then it gets written down on some paper that those are the right two values. And then it becomes part of somebody's program and the manual that's associated with that program. And pretty soon it's as though there was some real deep analysis that gave you that. So generally, the gap initiation should be more expensive. It should be more difficult to start a gap than to extend it. And actually, the 12 to 1 is actually some default values for some alignment systems that are out there. But in XParallel, you don't have to rely on that just single choice. You get to play around with what you think Y and Z ought to be. And in comparing proteins, these tend to be the two parameters to play with. What you have on spaces and what you have on gaps. Okay? So I want to show you a little bit more now about XParallel specifically. This whole business is called parametric alignment because we have parameters on portions of the model. Now, how well is that coming out in the TV version? Can you make that fill the whole space? See, I noticed that. And try to play whatever you can so this is most visible on the TV screen. Thank you. we're trying to maximize the value of the matches. And I say value now because that is implying we're taking the summed value from some substitution matrix, okay, minus the value of the mismatches. Well, again, whether this is a plus or minus really depends on what the actual shape of the, what the value is in the substitution matrix. But you should all understand that mismatches are bad and somehow they should be penalized, whether the value in the substitution matrix is written there negative, in which case you add here, or whether it's in there positive, in which case you subtract. You just have to be careful about what you're doing. Minus the number of spaces. We're going to have a multiplier alpha. Well, that used to, over here that was a y. Okay, now it became alpha. We all speak Greek now. Minus beta times the number of gaps. Okay? And so we have two parameters, and that gives us a alpha beta space for our choice of what alpha should be and what beta should be. The default in some systems has alpha of 1 and beta of 12, but in XPRL you get to explore the entire range of values in these two parameters in order to see what's the consequence of setting the values differently. And what do you get out of XPRL is you get a decomposition of the alpha-beta space into these regions, which are called convex polygons. And you can prove, that's not something we're going to do in this class, but one can prove that this decomposition has the following property, that whenever you pick a value for alpha and beta inside of a particular polygon, no matter what choices you make for alpha and beta, if they fall within the same polygon, then the same set of alignments are optimal for either point. Saying that slightly different, if I pick this point, for example, right here, and I find an optimal alignment for that choice of alpha and beta, the same alignment will be optimal for that choice of alpha and beta. There may be ties, there may be more than one alignment that's optimal at this point, but that other one, all of them that are optimal over here will be optimal over there. And by optimal, I mean they maximize. They make this maximization function as big as possible. So the polygon, inside of a polygon, it doesn't really matter what your choice of alpha and beta is. You're going to get back from the alignment algorithms. The alignment that maximizes the objective function will be the same one anywhere in here. Also, the converse is true. That outside of that polygon, no alignment that's optimal for a point inside the polygon will be optimal anywhere outside the polygon. Okay? So if I pick an alpha and beta here, and I find an alignment that maximizes the objective function for that alpha beta, I know for sure that that one will not be optimal over there in any other polygon. Okay? So what this decomposition shows you is exactly where the values of alpha and beta cause a real change. Okay? Inside one single polygon, you have a collection of alignments that are optimal. They're optimal nowhere else. And so this decomposition tells you how the optimal alignments behave as a function of alpha and beta. That's what XPRL does for you. Now, let me show you an actual picture. This actually is a little bit, this one is taken from a earlier version of XPRL. So what's up on all the choices up at the top are not quite the same as what you're going to have in your exercise, but all the important ones are there. And this is actually the final decomposition that you should end up seeing. And let me look for the Barton data. And let me show you the most important places to look. One of them is right here. And you can see that, there's one polygon that's shaded. And the alignment that's associated with the shaded polygon is shown up in the alignment window. So we're seeing up there an alignment that's got some, notice an alignment that's got some spaces in it, it's got some gaps in it. And here in this window that says VAR, it tells you how many matches that alignment has. If you can read this, it's 29. 29 matches. The next one is how many mismatches, that's 73. The next one is how many spaces, it's 16. The next one is how many gaps, that's 5. Okay? So in the alignment that's shown, which is optimal somewhere, well, it's optimal everywhere inside this polygon, you have those features, 29 matches. Yeah.
You said all the interior points within a polygon are as optimal as the other points. But what about the lines?
Okay, so the question is, what I said was that for any alpha beta point or xy point inside of the polygon, any two of them, the same alignment is optimal at one point will be optimal at the other point. And the question is what happens along a border between two polygons. There, all of the alignments that are optimal in the interior here, and all of the alignments that are optimal in the interior on the other bordering polygon are both optimal along this border. And similarly at a point, that's the intersection of more than two polygons, all of the alignments that are optimal in the interior of the polygons are optimal at that point. So you have a lot of different co-optimal alignments. Okay, so when you look at an XPRL display, you want to see what optimization did you choose. This is one that's called n-gaps free. I haven't explained to you. I should tell you what the terminology is. What we've seen so far, those alignments are called global alignments. Global because every character in the two sequences participates in giving the value to the alignment. Sometimes there's a belief that gaps that are at the ends of the alignments should not be scored. If you have one sequence much, much smaller than another sequence, for example, you're going to have very big gaps, probably, at the ends. And those are not necessarily meaningful. So there's a variant called n-gaps free. And XPRL XPRL gives you several choices. Another one's called local alignment, which we'll look at a lot in this class. At any rate, you'll see in your lab notes which variant to use. But here's where it shows what variant you're using. This shows numbers, matches, etc. of the alignments that are in this polygon. Over here, what this shows is, remember, the Barton data, you input aligned data. You input aligned sequences. In the file, you can look at that file, the Barton Go file. The two sequences are actually there as an alignment. There are spaces in them. That's the alignment that Barton thought was the right one from the basis of crystallographic studies. So we know how many matches, mismatches, spaces, and gaps that alignment has. So what's shown over here is the number of matches, mismatches, indels, and gaps that alignment has. It turns out that one in the Barton data has 30 matches, 72 mismatches, 16 spaces, and 7 gaps. Okay? The alignment we're seeing over here has 29 matches instead of 30, has 72 mismatches instead of 72, has 16 spaces, which is the same, and is organized into 5 gaps, whereas it's organized into 7. The alignments that are in here may not be the closest one, the most similar one to what was input here. In the current version, not in this one here, but in the one that you're playing with, there's actually a button that says, find the one that's closest. Forget about showing you the full decomposition. It just works until it finds one that it knows is the closest, and it stops there. But you can always sort of compare how the alignment that's shown here compares to what was input, if you have an input alignment. In the Fitch case, you can type in the sequences, there's no alignment given. Then what's down here actually tells you some numerical differences between the alignment at hand, here, and the input alignment. It says at point x, y, and I'm not going to tell you how it picks which points to look at, but at point x of 0 and y of 5, it picks a particular point. The value of the alignment shown up here, which is in here, well, this 0, 5 should be inside 0, 5. Yeah, sorry, 0 is x, and 5 is along there. 0, 5 should be in there. At that point, the value of the alignment that's shown up there is 941. But the value of the input alignment is 932, which is a numerical difference of 9, which is like 1%. Okay, so that's another reflection of the closeness of these two alignments, that this is a very small percentage difference between the two. Now, another thing that we have in the current version of XPRL, it's not in this slide, is something that's up here, which shows you the number of equally good alignments in each polygon. So, in this polygon, I vaguely remember there's either there's only one alignment that gives you the maximum value. It's optimal at every point inside here, but there's only one of them, or it's 18, I don't remember which. Some of these in here vary between 1 and 18. Okay, and then these buttons up here say next and previous, and you can scroll through the alignments. Sometimes the changes are quite subtle, but it'll show you the different alignments that are called co-optimal. And if there are more than 10,000 of them, it just says more than 10,000. And part of your homework exercise is to think about what does it mean if you've picked a model and a choice of weights where you're in a polygon with 10,000 equally good alignments. What does that mean about the value of this alignment as a tool to find biologically meaningful alignments? If there are 10,000 that are equally good under the criteria that you're working with, it's not a very precise tool. If you have only one, maybe the wrong alignment, but at least it's only giving you a few choices. Similarly, the question of how many polygons there are is the same issue. If there are too many polygons, then there's too much to explore. And then you can be a little more precise. If there are 18 in here, you can ask how do they really differ? Talking about computing the similarity of S1 and S2, two sequences. And remember the definition. We defined alignment. We've seen many alignments now. It's the max over all alignments of S1 and S2. Max of, now we're going to go back, for the purposes of beginning to understand how we compute similarity, we're going to go back to our simplest definition, even though last time we were talking about all the ways that are important in biology to make that definition more relevant. Maximum number of matches minus the number of mismatches minus the number of spaces, or indels. Okay? So this is our objective function. We want to find an alignment that maximizes this sum, and there are so many alignments that it's absolutely out of the question to have a method that would simply enumerate, look at all the different alignments, and calculate this value for each one. So we need an efficient method, a very efficient method. What does efficiency mean? Of course, it means, generally speaking, that it runs quickly, or that it doesn't consume a lot of computer memory, because that might be something else that isn't available. But certainly, time is important, or speed is important, and secondarily, memory, computer memory. Now, if we're talking about speed, first of all, you have to realize that the time that a program or an algorithm takes to compute something, to compute the alignment, the best alignment, the similarity value, is probably going to increase as the size of the sequences, the size of the strings increase. Huge strings, it just seems intuitive, we're going to take much longer to do those alignments than short ones. So when we talk about speed or efficiency, we're always going to talk about it as a function of string length or size. And just as we computed, when we calculated the number of alignments, we just assumed that both of the sequences were going to be of the same length. We called them n. So now we had a variable. We didn't talk about how many alignments are there when the two strings are of length 10 or so on. Well, that's what you can compute by the program that's available on the web. We had a parameter for those two strings. So one is length n, and the other one is length m. And they may both be the same in some of our discussions if we want to simplify things a little bit. But anyway, we have abstractly two lengths, n and m. And we realized that as n and m increase, certainly one could expect that the speed is going to, the time is going to take longer. It's going to be longer. The time's going to be longer. That's terrible. It's going to take more time, okay, as n and m increase. All right. But how do we actually clock that? Do we want to sit there with a real watch and talk about wall time? Well, that certainly is going to be dependent on what computer you actually run on, or other aspects of the computing system. So we want to be more abstract because we don't want to say, on your PC, that Pentium 2 is going to take this much time as a function of n and m, and on some other machine it's going to be something else. So what we look at is we use number of operations needed to compute similarity as a function of n and m. Okay, so that's how we're going to clock. That's how we're going to talk about whether a particular method is fast or slow. How many actual operations does the algorithm use to compute the similarity as a function of n and m? And what do we mean by operations? Well, that will depend on a particular algorithm. Sometimes it's additions, arithmetic operations, or comparison operations, or looking up a particular number in memory operations, things of that sort. All right, all this will become clear in a moment in this lecture, I hope. All right, now, okay, so that's what we're going to do today, is begin to talk about how we're going to compute similarity very efficiently. Now, it turns out that in all these discussions of algorithms and of alignment generally, it's very useful to use what's called an alignment graph. And alignment graph is really a very simple object, and I happen to have one here. This is an alignment graph for two sequences. This is what I'm going to be calling S1, Dan, and S2 is going to be the other sequence that's written there, S1, S2. So I'm interested in the alignment of S1 and S2 and computing the similarity of those two sequences. So what the alignment graph has is one column for each letter, and it also has a zero column. And for each letter in S2, it also has one row for each letter in S1, and it also has a zero row. Okay? Now, and then it has these little boxes here. Well, it has these nodes for every row-column intersection. So we have a total of 4 columns, numbered 0 through 3, and in this example, 4 rows, 0 through 3. And we have a node here at every row-column intersection. And then we have one of these little boxes for each 4 neighboring nodes. And the box just consists of an arrow that goes horizontally to the right, one that goes vertically down, one that goes diagonally, and then here's another horizontal, another vertical. And notice that there's a direction to each one of these arrows, and they all either go to the right, or they go down, or they go down and right. Okay? So now what I want to explain is that each path from the 0, 0 to this node over here, each legal path. A legal path is one that is obeying the direction of the arrows. Okay? It's not legal to go opposite an arrow. You'll get a moving violation that way. And each path from here to here that obeys the arrows describes an alignment. Okay? That's the first thing I want to claim, because that will help us later figure out what the best alignment is. So here's a claim. Okay? Each path from 0, 0 to NM. Okay, so we're starting at 0, 0, but we're ending up at the point that's NM. Little n little m for the lengths of the two sequences, i.e. the lower right node. Each such path defines an alignment of S1 and S2. And here's the way you do it. In that path, if you take any particular path, if the path goes along a diagonal, then we'll put the character that's on that row, you look at the node that the arrow is going into, the character for that row and the character for that column will be placed opposite each other. So that's going to be the meaning of a diagonal. Whenever you have a diagonal, we'll take the two associated characters and place them opposite each other. Remember, we're trying to create an alignment from a particular path. And I'll show you examples of this in a minute. Whenever you go along horizontal, okay, then into this node, horizontal, then you'll be placing the character in this column opposite a space. So in S2, you'll put the character of this column opposite a space into S1. So you'll make a space in S1 to be placed opposite that character. And whenever you go vertically, you'll be doing a symmetric thing. Vertically goes into a particular node, and the character in that row will be placed opposite a space in the other string. So I just have these three rules for how you turn a path from here to here. Any path you happen to find in here, how you turn a path into an alignment. Okay? So let me write this up and show you some examples. So a diagonal edge to a point, you have a character here and character there, means put character I of S1 opposite character J of S2. Okay? A horizontal, here you are in row I and you're going over to J, and here you put character J of S2 opposite a space in S1. And that space, we'll see, is going to come after, we'll see in a minute whether it's after or before character I. But as you're building up the alignment, it'll be right there wherever you're ready for next. And the third rule is symmetric. And then a horizontal from I to I plus 1 is going to be put a character I of S2 opposite a space in S2. Okay? So let's do some examples. What happens if I take the path that goes from 0, 0 directly? Just take the one straight down here to the lower right node. What alignment is that? That's just lining up all the characters opposite each other. So that would be S1, S2. Okay? So that's the path that goes like that. 0, 0, and M. Now let's be a little more inventive. What if we take the path that goes like here, and then a diagonal. So we're going here, diagonal, diagonal, and then down. What alignment does that correspond to? Well, one way of thinking about this, without looking back really at the rules, but it should be consistent with the rules, is that when I'm moving over here, really I'm using up a character of the top. A horizontal move means I'm using up a character in the top string, is S2. As I move further and further along, I've used up more and more characters of that top string. Similarly, as I move down, I'm using up characters of the string that's here along the rows, so that's string S1. So what happens if I make a horizontal move here is I'm using up the A from Ann, but I haven't used up anything here from Dan. So what does that mean? It means you're putting the A opposite a space. There's nothing being consumed in the second string. So this first movement here puts A opposite a space. Okay? Then we're moving down from here to here. All right? Well, that rule always was put the character here opposite the character here. We're now consuming two characters. So D gets put against N. Then we have another diagonal move, which puts N against A. All right? And we're here. And now we move down. That ends up using up this N, but nothing additional is used up from S2. So this N gets placed opposite a space. So hopefully what I said in terms of using up language is consistent with these more precise rules. The using up is really the right intuition for how to go from a path to an alignment. Okay? try another one, a rather silly one perhaps, where I go all the way down here and all the way over there. That's another path, right? So in that one, I'm using up the characters from S1 without using up any of the characters from S2. So they all get placed opposite spaces. That takes me down to here, and then from here I'm going over that way. And that's using up all of those characters, and of course nothing new from S1. So this alignment, this path, corresponds to that alignment. All right. Now, the claim is that each path gives you an alignment, and I don't know whether I said that those alignments are all different, but you should be able to see that every path, two different paths give you two different alignments. Just by seeing the rules here, somewhere, wherever those paths first differ, you're going to be doing something different at that moment. And so the two alignments are certainly going to be different. Okay? If two paths are different, maybe they begin the same, but at some point, one either goes along a diagonal and the other is a horizontal or vertical, so you're going to be doing quite differently there. Or one's a horizontal, the other's a vertical. Okay, so either way, you're going to see that the alignment will be different at that point, and maybe other places as well. But two different paths give you two different alignments. Now, what's the converse statement about these paths and alignments? Converse statement is that any two alignments, well, actually, any alignment corresponds to a path. Okay, so far, all I've justified is that every path gives you an alignment. But the converse is any alignment I show you, as long as you don't have a space opposite a space, every alignment I show you should correspond to a path. And the way you would do that is you start reading the alignment left to right, and you see, in that position, are there two characters opposite each other? If so, that's a diagonal. Is it a character opposite a space? Well, what character is it? I mean, where is the character in S1 opposite a space in S2, or is it a character in S2 opposite a space in S1? Depending on which it is, it's a horizontal or a vertical move. Okay, so every alignment gives you a path. And again, you should see the two different alignments give you different paths. Okay, because if they're different alignments, as you read them left to right, someplace they differ. And that means there's up to that point, the path that's being scoped out is the same, but at that point, where the alignments are different, the path has to differ as well. Because these rules tell you something specific to do for each case. All right, so I'm going to augment this. Each path from 0, 0 to NM defines an alignment, a different alignment, and each alignment, different or unique, each alignment defines a unique path, or distinct path, or different path from 0, 0 to NM. So when we're talking about all possible alignments, we're really talking about all possible paths in this alignment graph. And by moving over to this pictorial representation, it's going to simplify a lot. This pictorial representation is going to simplify a lot of our thinking about what's a good alignment and how we find it. It's going to be a lot easier to describe an efficient algorithm by looking at this than just doing it symbolically, although we will do it symbolically as well. All right, now in this picture, now stop me if anybody has any questions about this, because this correspondence is really the key. It unlocks a lot of intuition, unlocks a lot of the details of what we're going to come to next. Okay? So does everybody believe that when you go home and close your eyes and meditate on this, you'll see the correspondence between paths in here and alignments? It may not be crystal clear at this moment, but it has to be clear enough that you think you'll get it when you spend the time. If anybody's utterly lost, let me know. Okay. Now in this little graph, in this picture, let's call it graph, in the computer science world, there's three numbers that are written here. Okay? They're all number 1. And what they are, these are the edges that go into a node where the corresponding characters are identical. Okay? So this edge coming into here, this arrow coming into here, has an N associated with that column and an N associated with that row. And remember what the rules of the alignment are. If you go along a path that takes this edge, this arrow, you're going to end up putting N opposite N. So that's a match. And similarly, if you look over here, this is N opposite an N, that's a match. And this is A opposite an A, that's a match. And actually, those are the only 3 possible matches that exist. Every other diagonal in here specifies a mismatch. It ends up putting 2 characters opposite each other that are not the same, so it's a mismatch. Okay? And we already said that every vertical and horizontal, let me do that again, every vertical and horizontal edge ends up putting a space in. So we know spaces cost -1 in our original objective function that I started off the hour with, but it's now gone. So what I'm getting to is this. If you have a path that specifies the alignment, an alignment, and if you count a -1 for each edge that I did not put a number on, that was just for cleanliness, just to keep this from being cluttered. But if you put a -1 on every edge that doesn't already have a number on it, and you have a 1 on these 3, if you take a particular path from 0, 0 down to NN, and you add up the numbers that are on there, some will be 1s, possibly some will be -1s, but that sum is equal to the value of that alignment. Okay? So, alignment graph for strings, Dan and M, the weight on each edge is -1, except for the 3 edges marked in the figure which have weight +1. So just imagine that there's a -1 written on each of these edges where I don't have the +1. And then the claim is related to this one. 0, 0 to nm, the sum of weights on the edges. Edge, by the way, is just a mathematician's way of saying arrow. Okay? The graph world name for these things. The weights on the edges in the path. That sum is exactly the value of the alignment. Okay? So let's try a few examples like this one, or rather that one. So this is a -1, -1, -1, -1, -1, -1, -1. The sum along here is -6. And that's exactly the value of this alignment. Remember, you get a -1 for each space. You get a -1 for each mismatch, and a positive 1 for each match. So you get a -6. Now that we know that, what are we trying to do? And whose phone is that anyway? I don't think it's anybody in the class. So what are we trying to do? We're trying to get an alignment whose value is maximum over all possible alignments. The alignment whose value is the biggest over all possible alignments. So in terms of this picture, in terms of this graph, and knowing now what we know about the relationship of paths to alignments, what are we trying to do? What kind of path do we want to find from here to here? One that has a total sum that's very small, there's a small negative number sum, or what? What? Yeah, what we're trying to do is find a path from here to here whose sum, total sum or total distance is often called, whose total distance is as large as possible. Because each time there's a positive number, that's a match. Each time there's a space, it's a negative number. Each time there's a mismatch, it's a negative number. So we want a path which has a large positive value, or a large value. I mean, positive would be great. It doesn't have to necessarily be positive. So just eyeballing this, just looking at this, what looks like a good path? You'd like to pick up these two diagonals that have a 1 on them. It's clear you can't get all 3 ones. There's no way to have a path that goes through all 3 of these. But you can get 2. And what that path looks like is this. Okay? And so you get a +1, +1, -1. It has a total of 0. And what alignment is that? Okay? Using our rules, going vertically, you're using up D from Dan, but nothing from Dan. So that's a D against the space. Then you have 2 diagonals. So now you're placing characters opposite each other from the 2 strings. And finally you have a horizontal here. And a horizontal, again, means that you're using up something from S2 and nothing additional from S1. So that's the alignment that has value 0. And does it look like there's any path that gives you a bigger sum than this one? And just intuitively, it doesn't look like there's a path. Well, actually, we could make that formal because we've already said there's no path that uses all 3 of these. Okay, and every path. Now I better take it back. I was about to say every path has the same number of edges, but that's wrong. Okay, because this diagonal only has 3. But at any rate, this looks like the path that's going to have the largest possible value, which is 0. Yeah.
There's another path where equal.
There's what?
Another path that is.
There could be another path that's 0. Have you found one? What is it? Which one?
Down diagonal, right diagonal.
Down diagonal, right diagonal. Yes. Okay. So there's another one, and let's look at what that is. Down diagonal, right diagonal. Okay. So this is a -1, and this is a 1, and this is a total 0. And that one still has the same D, and the A with A, and all this is really doing is putting that space there and that one there. These are 2. The previous alignment and this alignment are co-optimal for this objective function. If you were to put this into X per L, Ann and Dan, with exactly this model of no weight matrix, okay, 1 for a match, -1 for a mismatch, -1 for a space, you should see that you would get in the right polygon these 2 co-optimals. Okay, so this relates to last lecture when we were talking about co-optimals. So these are equally good under this particular objective function. All right, so now we know what we want in order to find the best alignment. So, in order to find the alignment that maximizes number of matches minus number of mismatches minus number of spaces, try to find the path from 0, 0 to NM with largest edge sum, also sometimes called distance. It's hard to think of a negative distance. I mean, if these edges, anyway, that's the terminology. People talk about those things as distances. All right, now is this clear? transformed what an alignment is to this picture. We've now transformed the alignment question to a question in this picture. Did we make any real progress? We didn't have a method previously for finding the best alignment. Now we have a problem that's got different terminology, but are we getting closer to a solution? Yeah.
Why the abstract from 0? Why don't we just match change sequences?
You're asking why there's a 0, 0 in this graph? Well, the 0, 0 is so that we can have spaces put in one sequence before we're using any character of the other sequence. If I just had the graph without the 0 row, without the 0 column and 0 row, it would be starting here. And it would basically be saying I have to put D against A, or it would be hard to know what the interpretation is. But so far I've interpreted where you arrive to as what you do with the character for that row and column. What would you do with the D and the A if we started there? But having a 0 row says I can move along that row consuming characters from S2 without ever using anything from S1. So I'm putting spaces opposite those. Or similarly, going down the columns, I can do the same thing.
They're trying to create something for our message.
Sorry, what?
They're trying to create something for our message by inserting two spaces between them. Right? They're inserting two spaces in sequence right at the beginning before we make anything else.
I didn't catch that, but I think you're right. Yeah, sorry, I didn't really hear it clearly. I'll remind you to try to speak in your microphone, which will help me and the listening audience at home.
I'll ask about it later.
Okay, good. All right, so now we have this problem. I want to find the path that goes from 0, 0 to NN with the biggest total sum. And I could, again, just enumerate all possible paths, but we already know. Well, how many possible paths are there, by the way? Does anybody either know a formula or know where I can find a formula for that? Yeah.
It's on all the ways you reach certain points and add it up.
We could, what you're saying is, think about it. We could do that, add it up.
For example, for the 0, 8,
Yeah.
there's one path to that point. And the diagonal, then you calculate how many paths you can get to that point.
Yeah.
And just keep adding up.
Yeah, that's true. We could get a recursive kind of approach to counting how many paths there are at each point. But there's a simpler way. I want to know how many paths are there from 0, 0 to NM. And I don't want to do a lot of work right now. I just want to turn a page, perhaps, and find it. Yeah. It's what? N times M?
Yeah.
No, N times M, no. Too small. What?
Exponential
Not right. Yeah, maybe, yeah. It's what? 2 to the N plus M? 3 to the N plus M? No. 2 to the N plus M? No. Okay, here's the point. We, today, argued that every path gives you a different alignment, and every alignment gives you a different path. So the number of paths is exactly equal to the number of alignments. Okay? There's a one-to-one correspondence between each path from 0, 0 to NM and a different alignment of S1 and S2. Okay? That's the whole point of today's lecture, essentially. And we've already come up with a formula for the number of alignments. I don't think you have to know it off the top of your head. But we already have it. It involves a summation of product of factorial, number of coefficients, and so on. So the number of paths is exactly equal to that same formula we already had. Okay, that's the answer I was looking for. Okay. So we can't, again, for the same reason, we're not going to try to enumerate all those paths. But actually, somebody suggested how we could calculate the number of paths sort of on this picture here. And that turns out to be a very useful observation, which leads us really to how we're going to calculate the path that has the biggest sum. We're going to say, what's the best sum of a path that goes from here to here? Of all the possible paths that go from this one to itself, what's the biggest possible value you can get? 0, because really the only path is just to sit there. Because of the way the edges go, the arrows go, you can't do anything else. Then we're going to ask, what's the best possible, by best I mean what's the biggest sum we can get in going from here to here? Minus 1, actually, there's only one way of doing it, okay? What's the biggest number I can get by going from here to here? Minus 1 again, because there's only one way of doing it, all right? Now, what's the biggest number you can get by going from here to here? That's minus 2. Again, there's only one path that even gets you that way because of the way the arrows go. That's all you can do. And similarly, to get to here is minus 3. And to get to here is minus 2. And to get to here is minus 3. Okay? So the method I'm trying to introduce now is going to finally figure out what's the best way of going from here to here by figuring out what's the best way of going from here to each of the other possible points in this graph. And the way we start is with the really easy ones. The easy ones are the ones I just did, along the first row and along the first column, or the 0th row and 0th column. Okay, now I can ask about this one. What is the, of all the paths that can take you from here to here, what's the path with the largest sum? It has a minus 1, just go directly, because if you went this way and this way, it would be minus 2. Or if you went this way and this way, it would be minus 2. So this one has a minus 1. Now, you can see that directly by saying, okay, the path was either this one or this one, or the path was this one or this one, or the path was that. But the way I really want you to think about it is the following. To get here, because of the way this graph is laid out, you either have to come from here, your nearest node, your last node you're in, before you get to here, either has to be this one, or it has to be this one, or it has to be this one. If your last, in either case, well, if the last node that you visit before you get here is this one, then the total distance to here that way is the total distance to here plus what's on here, which is -1. If you come through this node as your last node, then the distance along that path is whatever the distance was to here, which is -1, plus whatever the distance is along this edge, which is -1, that's -2. The similar reasoning tells you this is -2. Okay, let's make this a little more interesting, perhaps. Let's say I want to go from here to here. That's the best way. That's the path with the largest sum on it. I don't want to think about all the possible paths that get you there. Already we're seeing that's growing to be a large number. I want to apply that logic I just went through. The logic said, if I'm going to get here, the last node I visit before I get there either has to be that one, or that one. Because that's the way the graph is laid out. If it's this one, then the total distance of that path would be whatever the distance was to here, which I know was -2, plus this distance along this edge, which is -1. So that would be a total of -3. If it's this one, it's the distance to here, which is -1, plus this edge distance, which is another -1, that gives -2. If it's through here, it's the distance to here, which is -1, plus that one, which is -1. So I have three different numbers to think about. -1, sorry, this way was -2, this way is -2, and this way is -3. What's the biggest of those? -2. So this one gets a -2. And the main thing to point out is that when I was figuring it out, I didn't think about all the different possible paths from here to here. I just thought about three cases. Either the best path came through here, or came through here, or came through here. Now, if you think about this and continue it, you'll see the idea of an efficient algorithm. But we will pick this up next time and do it in complete detail. The question we started talking about last time, which is how to compute the similarity between two sequences, how to compute it efficiently. And what I did last time, remember, is I defined and described this thing called an alignment graph, and then we saw that there was a one-to-one correspondence between alignments of the two sequences displayed on the alignment graph and paths in the alignment graph from the upper left-hand corner to the lower right-hand corner. And that correspondence really helped clarify our thinking about alignments and how to compute good ones. So I'm going to go back to pretty much where we stopped last time. Get the screen. Okay, so here's the alignment graph we were dealing with last time that aligns Dan and Ann. And what we said again was that every path from the upper left-hand corner to the lower right-hand corner in this alignment graph specifies an alignment, a unique alignment. Every two paths that are different specify different alignments. And conversely, every alignment corresponds to one such path, and two alignments that are different correspond to different alignments, different paths. And then we introduced this notion of weights, or distances on the edges. So a distance of 1 meant that the edge that went into here corresponds to two characters that are the same. So this is a match. There's another match, or you can call it a potential match if it's used in alignment. Every other edge that doesn't have an explicit weight on it is assumed to have a -1, which really means it's either a mismatch, like this one is, and opposite D, that's a mismatch, or it's a horizontal edge, which means it's a space that's being introduced in the alignment, or a vertical edge, which is also a space introduced into the alignment. So we ended up last time by saying, if you can find the path from here to here with largest total sum, that path specifies the alignment that maximizes the objective function that we're interested in. Without writing it up on the blackboard again, it maximizes the number of matches minus the number of mismatches minus the number of spaces in the alignment. Okay, so then we got into the question of how do I find that path, or a path, there may be ties, how do we find a path that has the largest total sum, or largest distance from here to here? Okay? And I started introducing this sort of procedure, which was, it follows the following idea. I really want to compute the longest path from here to here, and the way I'll do it is by computing the longest path from here to each of the other nodes in this alignment graph, ultimately finding the longest path from here to here. So we start with the really easy questions. The really easiest question, what's the longest path from here to itself? That's at length 0, and the path itself is just to sit there. Okay, you can't go anywhere and come back, that's just the way the arrows are pointing. And then another simple question is, what's the longest path from here to here? Again, there's only one, the first, and its distance is -1. That was what's written here. This -1 is not for this edge, but for this node. Then we ask, well, what's the longest path from here to here? And again, the only way to get to here is through there, through this node. And so it's -1, which is what it was to get to here, minus another 1, which is what happens along this edge. So the total for here is -2. That's what's written here. Again, it's -2 is for this node, and not for that edge. All right, we continue. What's the longest path from here to here? What's the distance of that longest path? And again, the only way to get to here is through there. And we know that the longest distance to there is -2, and the distance along this edge is -1. So the longest distance to here is -3. Okay? So now I've figured out what the longest distance is to each of the nodes along the first row, or the 0 row. And I can do a similar thing along the 0 column. Okay, so those are the easy cases. Ultimately, remember, my goal is to figure out what the longest path is to each one of the nodes inside here, in particular that one. And what's the next easiest case? Once I've done these guys and these guys, well, it's this one. Because the way you reason is that to get to here, the only paths either go, the last node that is before I get there either go through that one, and I know what that distance is, that's a -1. So if I take the path that goes through that one, that's -1 with another -1, which would make that way -2. That's one possibility. Or it's to go this way, because this is the last node visited before this one. This one is a 0 with a -1, so that possibility gives you a -1. Possibility coming through here is also -2. So the largest over those three possibilities, -2, -2, and -1, is the largest is -1. It's easy to get confused and talk about and think about absolute value and say, no, the largest is -2. No, the largest is -1. So I now know what the distance is to here. It's -1. Okay? Now let's look at this one. This is a little bit more instructive to look at this guy. Again, the reasoning is going to be this. To get to here, the last node I visit, if I think of all the possible paths that take me from here to here, the last node I visit before this one is either this one, or this one. Three possible neighbors. That's important to keep in mind. If the path I take goes through here, then the distance is -2. That's the longest distance to get to here. With another -1, so that would be a -3. If it goes through here, that's a -1. With another -1, that's a -2. And if it goes through here, it's a -1 with another -1, that's a -2. So you have three possibilities, -2, -2, and -3. The largest of those is -2. Okay? Let's just do one more before I make my main point. Let's try that one. What's the longest distance to there? Well, either that path, the best path that gets to here, either goes to that node, in which case its distance is -3, -1, which is -4, or it goes to that node as the best node before it reaches there, which is a -2, -1, which is -3, or it goes to there, which is -2, with a -1, which is -3. So again, we have three possibilities, -3, -3, and -4. The largest of those is -3. Okay? Now the key thing I want to point out here, and it's true everywhere else, is that when I figured this out, after I had already done the three neighbors, I didn't have to, when I'm trying to figure out what's the longest path that gets me from here to there, I didn't have to think about all the possible paths. I didn't have to enumerate all the paths from here to there. Even though this is a small slice, there are a fair number of paths. We can figure out what it is, but it's certainly better than 3. Okay? I didn't enumerate all the paths that went from here to here and fully calculate all the distances. But what I did was only 3 kinds of operations. I said, whatever that path is that goes from here to here, whatever the best path is, in fact, any path that goes from here to here, the last node it visits before reaching here is either this one, but I already know what the largest distance is to there, so I would know that any path that goes through there before it reaches here has a distance of -4. Or that path goes through here, in which case the largest distance that goes through here is -3, and similarly, it might have gone through here, in which case the largest is -3. Point being that when I'm focusing on this node, if I know already the longest distance to its neighbors, the amount of effort I'm making here is just basically looking at 3 pieces of information, 3 numbers, doing 3 additions, and then making a comparison between 3 numbers. So that's 9 operations or 8 operations, however you count them carefully. It's just a handful of operations. Okay? And it doesn't matter how many paths there actually are from here to here. The number of operations I do when I'm focusing on this node is just that 8 or 10, whatever that small number happens to be. Okay, let's just continue until we get down to here. What am I next ready to do in this picture? Which node is next ready to compute, or are there choices? I think there's only one node that we're ready to compute, whose distance we're ready to compute. Which one is it? It's what?
The third or second?
Sorry, what?
2, 3. I think 13.
3, 2, 2, 2. This one? Okay, this one. All right, we're ready to compute the distance to here because we have the distances to its 3 neighbors, the 3 neighbors that point into it. That's the key thing. When you're looking at a node in the alignment graph, you're ready to compute the longest distance to it from this origin, provided you have the longest distance already computed to the 3 neighbors of that node, the 3 neighbors that point into it. Okay? So, looking at this node, the longest path to it either goes through here as the last node before it reaches that, in which case it would be this